Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady. Now in Module 7, we're going to talk about a virtual memory. And the first section of Module 7 is Principles of Virtual Memory. We're going to actually define what is a virtual memory and what is virtual memory is used for. Now, in Module 6, the memory management, we mentioned that once a process is created, it will be first placed in the logical memory space before it is loaded into the physical memory. Okay. Logical memory space. Now, using one of the approach, the paging, a process is actually divided into pages, right? So in this particular case, we divide this process into 1, 2, 3, 4, 5, 6, 7 pages, starting from 0, 1, 2, 3, 4, 5, and 6. Now, before we load the process into the physical memory, we need to check the physical memory to make sure the physical memory contains enough space for it, right? Using paging, the physical memory is also divided into a partitions called frames. It's called a page frames. Okay, so I have a frames at number 0, 1, 2, 3, and maybe n-1. Okay, so in order for us to load the process into the physical memory, we need to check whether there are enough frames to accommodate the logic space. Now, in this case, we need to find out 7 physical, the page frames, 7 free page frames. So then we can load each page into a frame. Okay, so in this approach, we assume that the logical memory space is always smaller than the physical memory. Okay. Now, in reality, in many cases, we can actually execute the process which is much larger and sometimes even larger than the physical memory space. How can we do this? So let's assume that now we have a logical memory space, which contains up to n-1 pages. So that means for this logical memory space, we have n pages. So in here, there's m frames, right? Now, in some case, the n could be bigger than m. Now, how is this happen? How can we actually do this? Now, we're gonna do this using the concept of virtual memory. Okay, what is virtual memory? So virtual memory is a collection of one or more logical address spaces, each of which may exceed the size of physical memory. Okay, now in that case, the logical memory is sometimes also called a virtual memory. So basically, a paged virtual memory creates a single large contiguous address space per process. Now, how can we do this? Because based on our understanding in Module 6, if we want to run this process, we have to make sure we have enough physical memory space to load this process. Now, in this case, the process is much bigger than the physical memory, so we should reject this process. How can we, still run this process? So here we're going to use one of the approach called demand page. Now the demand page is the principle of loading a page into the memory only when the page is needed, rather than the start of the execution. So we don't actually load all the pages into the memory, because in this case it's impossible, right? However, if we actually, when we start to execute a process, we may actually, just execute a small part of the process. For example, we're going to start from the main program, right? And then for some of the other component, like a subroutine, a process, some of the dynamic data, they haven't been created yet, or even even if they are already there, so we don't need to execute this piece of code, like some of the functions, subroutines. So we don't load this part of the process. We only load the main program. So we start to, and the main program may only requires, for example, 3 pages, right? So then we can first load 3 pages into the physical memory and start to execute the instruction in these pages. And then during the execution, when this page, these instruction requires to try to refer some of the memory space in, some of the memory actually instructions located in other pages, then we load the other pages. We slowly load more and more, and hopefully, after for a while, some of the pages we loaded earlier has been completed, right? All the instructions in this page has been completed. So we can actually, remove these pages and free up the memory space and load some other pages. Okay, so we don't load all the pages at the same time. Just load, when we actually run the program. Now, in this case, there's a chance, there's a possibility that we can run a process which is much bigger than the physical memory can accommodate. So the demand paging makes the implementation of virtual memory possible by moving pages to the main memory only as needed. Remember that if we have a process here, okay, this process is going to make, contains, let's say, n-1 pages starting from 0. Okay, so then we know that the operating system memory management use the page table, right, to track which page is in which page frame in the physical memory. Okay, so here's a page 0, 1, 2, 3, 4 with a process of n pages. Then the page table should contain n array, right? So it's n-1. Okay, that's n page minus. So as we mentioned that we cannot load the whole process into the computer physical memory, because the physical memory could be smaller than the process. Okay, that's the page frame numbers. So that's m page frame. Page frames, right? So now let's assume that n is bigger than m. Okay. So now in this case, using the demand paging, so we can say, oh, maybe initially we just need to execute page 0, page 1, or maybe page 2. So then we can load page 0 into frames. Let's say, let me actually change the color so we can clearly see which page load into which frame. Okay. So let's say page 0 is loaded into frame number 1. Okay, so that's frame number 1. And then page 1 loaded into frame number 10. And page 2 loaded into frame number 2. Okay, so then we can actually update the page table, right? So so page 0 loaded into frame number 1, page 1 loaded into frame number 10, page 2 loaded into frame number 2. Okay, so we can update some of the page table item. But for page 3, it's not loaded to any physical page frames yet. So in that case, so the other pages, we cannot fill up any numbers because they are not loaded yet. So the page table doesn't show the the corresponding frame number. Okay, now how could the operating system manage this case? Okay, how does the operating system manage this case? So the operating system use another 1 bit in the page table. They create another bit. Okay, for each item, it creates another bit. It's called a present bit. Okay, so that's page number, that's frame number, and that's called a present bit. Now the present bit is just 1 bit. Basically, it's used to reflect whether this page is loaded or not. Okay, now if a page is resident, it's loaded into the memory, then we can actually put that number 1 in there. This one is loaded. Okay, this one's 1. Okay, now page 3 is not loaded into the physical memory yet, right? So it's not there. So we're going to use the present bit. We set the present bit to all to 0. Okay, so it could be 0. It's all 0. Okay, so the present page basically indicates whether this page is currently resident in the memory. Okay, so that's good. So then we start to execute the instructions in page 0 and then page 1, page 1, page 1. So then we use the page table and map the page table to a frame number, and then we copy the offset, right? Remember how can we map the logical memory address into the physical memory address? We use the page table, right? So we use the page table and then find the corresponding frame. Then you, based on the offset, we just copy the offset. We can, locate the physical memory address. Okay, now we continue to run, and then after actual page 2, we start to run an instruction which is located in page 3. Now what happens? So the operating system check the page table. Okay, so then it just checks the page table, say, okay, page 3, and it will first check the present bit, right? And the present bit says 0. That means, okay, so this page hasn't been loaded into the physical memory yet. Okay, now what happens? There's going to be an error, right? And in this case, so the error going to happen. So this is called a page fault. Okay. Now a page fault is, so basically, so the operating system is going to say, no, this page is not loaded yet. Okay, but the operating system is not going to actually interpret this as system error. It's not going to stop the execution. The operating system is going to trigger an interrupt. Okay, that interrupt is called page fault. Okay, so page fault is an interrupt that occurs when a program attempts to reference a non-resident page. So in this case, page 3 is non-resident page. So the interrupt triggers the operating system to find a page. So the operating system is going to say, okay, so page 3 is a legitimate page, but it's not loaded yet. Let's try to find a free frame. Okay, can we find a free frame? And then, yes, we find a frame over here. Let's say frame number 15. Okay, it's free. And then we load page 3 into the frame number 15. Sorry, it's 15, not a 3. So let me erase this. Okay, so we can update this into 15. And then also, don't forget to update the present bit from 0 to 1. Okay, we have to update that information as well. Okay, so then it starts to do the mapping. So then if we want to execute this instruction in page 3, and then I'm going to say, okay, using the page table, 3 is mapped to 15. And if this is the first instruction, so then check the offset, which is the first instruction in this frame number 15. So we're going to continue to execute. Now this way, the page table may grow bigger and bigger and bigger. Okay. Now, sometimes things are gonna happen that so when we trigger the page 4, then page 4 is not loaded. So we try to find a physical memory space and to see whether there's a free frame, right? If there's a free frame, we load actually the 4 into the frame and update the present bit into 1. So we keep doing this, but remember, you cannot continue to do that because the number of pages actually exceeds the number of frames. So sooner or later, we're going to run out of physical memory space. Now, in that case, what happens? That's something we're going to discuss later because we're going to actually use an approach called page replacement. So remember, if you try to actually run a page, run an instruction in a page, and the page is not loaded into physical memory, and we try to look at the physical memory, and there's no free frames in the physical memory. Now what happens? We have to kick some of the pages out of the physical frame. Okay. Now, which page we need to kick out? We hope that we can kick out the pages that hasn't been used for for a long time, right? So we try to kick out some unused page in the physical memory and then load this page into the physical frame. That's called a page replacement. Okay, so let's summarize what we discussed in the previous slide. Now we learned that a virtual memory can be bigger than the physical memory. Okay, so let's say the virtual memory consists of n pages from page 0 to page n-1, right? And the portion occupied by the program, from page 0 to R, is kept on disk. So we keep this on the physical disk, and the remaining page are just an abstractions. So that means they're there. That's part of the program, but they are not loaded yet. So the page table keeps track of what pages are currently in the physical memory using the present bit, right? If the present bit shows 1, so that means that page, the corresponding page, for example, page 2, 3, and the K and R, these 4 pages are in the memory. Okay, they are resident in the memory. Okay. Now, if the execution crosses the page boundary, so for example, if we execute the page number 3, okay, suddenly we cross the boundary, so we actually run into page number 4. And number 4, we find out, okay, number 4 is not, the present bit is 0. So it's not in the memory. It's not resident actually in the memory. So now what happens? The page fault happens, right? Now page fault is an interrupt. This interrupt can actually eventually just actually try to find a physical frame in the physical memory. And if we find a free frame in the physical memory, and then we load the page into the frame and update the page table, right? For example, we find, okay, frame number 3 is available. So then we load this frame number 3 over here, and we update this present bit to 1. Now, of course, in this case, page 2 is loaded into frame number 2, page 3 is loaded into frame number 0, and the page K is loaded into frame number 5, page I is loaded into frame number 4, right? So now we load the page 4 into frame number 3. And then page 4 is now resident in the memory. So when we actually execute the instruction in this page 4, then we use the page table and locate the frame number, right? We locate the frame number and then use the page table and find the frame number, and then we just copy the offset. So this particular logical memory address is going to be mapped to this particular physical address. So this is how we're going to do. We can continue doing this way if the page is needed, but it's not in the physical memory. Then we have a page fault, and the page fault is going to find a free frame and load this page into that free frame and update the page table and update the present bit from 0 to 1. Okay. Now remember, sooner or later, we cannot continue to do this because we assume that the logical virtual memory, the logical actually memory space is bigger than the physical memory. So eventually, you cannot fill up the page table completely because sooner or later we're going to run out of physical memory. Now, if that kind of things happens, what are we going to do? Then we're going to use another approach called page replacement. So suppose we are run into a page, okay, and then we find out that page is not in the is not resident in the memory. And then we have a page fault and try to find a free frame in the physical memory, and we could not find a free frame because all the physical memory frames are full. There's no physical free frames left. So what happens? Then we need to use the page replacement. Then we need to find a victim. So we need to locate a page that is currently in the physical memory, but we think this page has been used and then no longer needed. So then we can actually swap that page, So we kick the page in the memory out, and then load this page into the physical memory, and we update the page table and replace the, so what we're going to do is, for example, so this page is r+1. So r+1 is called, and r+1 is not in the physical memory, right? So then we find a page, say, okay, page 2, is not in use. We want to replace it. What are we going to do? So we can actually change the present bit to 0. Okay, so make this page, we kick that page out, and then somehow we just update, put the page 2 in here and replace that one with 1. Okay, so now frame number 2 is currently mapped by page r+1, not page 2 anymore. That's called a page replacement. Now there's some kind of issues with page replacement we need to resolve, but that's the idea of the concept of page replacement. So page replacement is the act of overriding a page in the memory with a different page loaded from the disk when needed. Okay, so for example, here's the virtual memory, and then these are the pages, right? And here it is physical memory, and these are the frames. Okay, so then if a particular page 0, 1, 2, 3, for example, page 2 is called, and the page 2 is not currently in the physical memory yet, based on the page table. So page 0, 1, 2. So then we use the bit, present bit to indicate the page 2, which is currently not in the physical memory, and pages 0 and 1 are in the physical memory. So the present bit is set to 1 in these two cases, but page 2 is not currently in the physical memory. So then page fault happens, and then we try to find a free frame, right? We try to find a free frame. So then we load this page 2 into that particular frame, and we put the frame number in the page table and update the present bit from 0 to 1. Now, if no such a free frame exists, so that means the physical memory is full, then we need a page replacement, right? Now, we mentioned that we can actually try to locate a particular frame which contains a page, certain page. I don't know, page, say page I, so which represent the, page number I, which is currently in the physical memory, let's say in a frame number J. Okay, so page I is in frame number J, so the present bit is 1. So now we identify this page I, so we replace the page I with page 2, for example. Okay, so what are we going to do? So we're going to kick the page I out and put the page 2 in there, and so then here is the J, so we update the frame number and update the present bit to 1, and then we're going to actually update this present bit to 0, right? So page I is no longer in the physical memory. Now, when we actually kick a page I out, we cannot simply kick it out, just wipe it out, because maybe page I will be needed again. So the page I need to be loaded back into the memory again later on. So you cannot kick them out, right? Now, in particular, if once the page I is loaded into the physical memory and the page I has been modified by the program, so then the page I in the physical memory is not the same as the page I in the virtual memory. So that means before we try to kick the page I in the physical memory out, we have to copy the value of page I into the virtual memory. So we have to copy it back to the virtual memory. Okay? Because once we load it back, we have to load the page I as it is. You cannot actually load the original page I back to the memory. Okay? So how can we record this? How can actually the operating system know whether this page has been modified after it's loaded into the physical memory or not? Then we use another bit in the page table called modified bit, or it's called M bit. And the modified bit sometimes is also called dirty bit. Okay. So the modified bit is set to 1 automatically by any instruction that stores the data into the page and is used by the operating system to minimize the movement of the data to the disk. So, for example, if page 2 wants to replace the page I, right, which is currently in the page frame J. So now, if page I has been in the physical memory and the page I has never been modified, so that means the value stored in page I is the same as the value in the virtual memory. So in that case, you don't need to do the copy, right? In that case, you can now really kick the page I out, because later on, when the program actually need a page I again, you just load the page I in the virtual memory back. You don't have to, worry about whether page I should be copied back or not, because it's never been updated. So that modified bit is very useful. It's going to save a lot of time. Okay, let's discuss how the page replacement works. Okay. Remember, here's the virtual memory, and it contains n pages, right? From page 0 all the way to page n-1. And initially, only 3 pages are loaded. Page 2, 3, and K. So now page 2 is mapped to frame number 2, right? Page 3 mapped to frame number 0. Page K maps to frame number 5. Okay. Now remember, we use the present bit to indicate that which pages actually is resident in the memory. So in this case, initially page 2, 3, and K are in the memory. So we actually use 1 to represent that it is in the memory. And also with the page replacement, we use another bit called modified bit, right? Also we call it dirty bit. So the modified bit to keep track of which pages has been modified. Okay, so initially, once the page 2, 3K are actually loaded into the physical memory to different frames in the physical memory. Now, this page hasn't been modified yet because, initially, right? Now, after we execute the instructions in this page, page 2, page 3, and page K, now certain of the data in the page may be modified. So if the data in the page is modified, then the modified bit will be changed from 0 to 1. For example, if page 3 which is currently in physical frame number 0 is modified. So that means page number 3, that's the initial state. In page number 3, and there's one statement say x is initially 0, for example. So we load page 3 into the physical memory, then the x equals 0. And during the execution, the value of x has been changed to, for example, 4. Now, then we have to actually modify this modified bit from 0 to 1, because once the page 3 is loaded into the physical memory, the data has been changed. Why we need the modified bit? Let's take a look. So now suppose I want to actually load another page. For example, page R want to be loaded. Okay, so then the operating system actually try to execute the instruction in page R and find out, look at the page table, and then find out page R is not loaded. Okay, because the present bit is 0. So, and then the page fault happens, right? The page fault. The page fault, which is an interrupt that eventually gonna, try to find a free frame in the physical memory. And if unfortunately we could not find any free frame, so that means the physical memory is full. So then we need to execute the page replacement. Now, if for whatever reason we use a page replacement algorithm and we identify that we want to replace page number 3, which is currently in frame number 0. So then, before we replace the page number 3, which is in physical, frame number 0, so you need to check the modified bit and find out, oh, the modified bit is 1, so that means this page has been modified, right? So before I replace the page 3 in frame number 0 with page R, I have to copy the data, copy this page back to the virtual memory space. So then that value x is going to be updated to 4 because you're going to copy the values from here. And then once it's copied, then the next thing we're going to do is then I can, replace this page number 3. Okay, I changed the color so I can clearly show the differences here. Okay, I use the orange here. So I want to replace it. So I actually load the page R. Once it's finished the copy, and then I load the page R into the frame number 0. So now I update the page table. So this now the frame number is, so let's see. I use different color. That color is not really good. Okay, so I'm gonna load page 0. So that's a frame number. Now that's the page number, right? So this is a page number. Okay, so that's the present bit, and that's the modified bit. Okay, present bit number. So then I load this, and I update this from 0 to 1. So the present bit becomes 1, and the modified bit is 0 initially once it's loaded from the virtual memory. So it's not modified, right? So it's 0. And then I'm going to update this. So this 0 doesn't mean anything. It's no longer valid one. So because I can replace this one to 0. Okay. If this is 0, it really doesn't matter what is this. You can actually set this back to 0, right? So now, because the present bit is 0, so that means the page 3 is no longer in the memory. Now instead, this page R is in the place where the page 3 used to reside in. Okay, now that's why we need the modified bit. Okay, so if the modified bit is 0, and if we want to replace the page which is currently in the computer memory, and that page has modified bit 0, so that means you can simply replace this page in the physical memory without copying the value back to the virtual memory, because there's no need to do this because it's not modified. So the page in the physical memory is the same as the page in the virtual memory, right? Thank you.